I'd like today to put in use the things that we were talking about this morning. This is module 5.3. It's going to be integrating network models with multicellular models. And I'm going to be focusing on a particular example. So this is going to be, like many of our afternoon talks, a bit of a coding example, which is the delta notch signaling, which is a problem that absolutely requires multicellularity and network models and coupling between cells. And we'll see how far we get with it. There are a bunch of exercises. All of the exercises are available already completed in the student materials folder. The numbering may be slightly different, but I'll show on the slide what the number is. And so if people get stuck on one part of the exercise, then you can continue with the remainder without getting behind. And I also want to say that if we don't finish all the exercises, they're great homework problems. And I'm actually at the end going to allude to a problem that I'd like people to maybe to try out over the weekend if they have time to consolidate their experience. As always, I need to remind you we're live streaming and recording this. We're going to quickly remind ourselves of antimony syntax and how to use antimony in CompuCell, since we went over that pretty fast this morning. And then I'm going to talk about delta notch, and we'll build the delta notch model. And if you're interested in more detail, the 2023 lectures cover things in a little bit more detail. And again, you can find the demos to download, CC3D demos, and they'll be all there. I would encourage people to do that so you don't get stuck. So just to remind you on antimony usage, remember that in the twitted code snippets, the antimony is hiding under the pull-down SBML solver. And so if you look for antimony, you're not going to find it. We should really rename that network solver, but in any case, it says SBML solver today. And so you have to remember that it's hiding there. As before, I like Herbert's textbook. There are many other textbooks. If you want a basic guide to using antimony, the Quick Start Manual, if you search tellurium antimony, read the docs, Quick Start, you'll find it. Has great exercises. There are many other textbooks on dynamical modeling of networks, but this one I think is really simple and very clear. Remind you that we only need a couple of things to do antimony syntax. Antimony models go inside of triple quotes. // and hash are comment characters. Semicolon is a delimiter. Colon gives a name to a rate law. Chemical reactions written as name, colon, X goes to Y, semicolon, rate, semicolon, are the fundamental declaratives in antimony. And you need to always define the parameters and initial conditions for your variables as well. If you want to, you can write ODEs directly, but we don't encourage that. Again, if you're using the code snippets, the code snippet you have to pull down is SBML Solver, and you'll see model initial data, add antimony model to cells by ID, add antimony model to cells by type, add antimony model to individual cells. Those are all pretty useful. Add cell ML models, add SBML models, add free-floating antimony model, add time step SBML models, and that really is any network model that you've loaded. Copy SBML model, delete SBML model, set integrator options, and a variety of other things here. Get value and set value are important if you don't remember how the dictionaries are defined. So that's a long list. Again, the SBML may be a little bit distracting. Just remember that in our world, SBML is a synonym for antimony. but you could in fact use SBML models if you prefer. So once you've decided to do that, again, integration is through Python. We mentioned you can load antimony models into entire simulation. That's what we did this morning. Today, we're going to load them into individual cells. Remember, all antimony models and parameters are CC3D dictionary entries. That's how we're going to interface with them. You're always going to need to remember to time step the antimony model in the step function in your Python. Don't call the step function this time stepper more than once per time step. It's a common mistake to put this time step model inside of a loop by accident, and then you have issues. You can decide whether you want to solve those antimony models deterministically or Gillespie. We did that this morning. Okay, remember, you're going to define your model string. I tend to call the string just model. That maybe isn't such a great idea. Self.add antimony model to cell. In our case, we're going to be adding it to individual cells. Model string equals, and then in this case, whatever we called it, the variable name model. And then model underscore name equals some string, which is how we're going to refer to that model in CompuCell. The identity of the cell, it's a handle for the cell, and then the step size. In principle, we can have many individual models loaded into one cell. We can have many copies of the same model in different cells, and we could assign different step sizes to different cells or to different models. So there's actually rather a lot of flexibility. I'm not recommending that you use that flexibility right at the moment. One thing that's a useful thing to do at the beginning of your code is to define some conversion factors. Here I've said seconds to Monte Carlo step is 5 times 60 seconds per Monte Carlo step, days to Monte Carlo steps, S underscore to MCS divided by 60 divided by 60 divided by 24. And then within the then we also have said SBML step size is days to MCS, for example. So I encourage you to define here in the header of your CompuCell. Those things that are in the header are available in the classes, but not writable as parameters. That's a good place to do conversion factors. That's good practice. We should probably have those populated automatically, and we're working towards that, but it isn't there right at the moment. So again, you're going to be defining the antimony model. The antimony model also will go in this header region of CompuCell before the class definitions, ideally after the parameter definitions, right there. So here I've pasted in, I've named the model something else, ODE model string equals triple quotes, and then my antimony. This is an example of a rather complex model of semitogenesis. In this case, this particular paper predates our support for SBML, so this was hard-coded as ordinary differential equations. One of the reasons I'm so aware that you shouldn't write ODEs to begin with is our experience with this model and the difficulty people had then adapting it and reusing it later. We've recoded it over the years. This wouldn't be a bad hackathon project, actually, to build an SBML or antimony-based version of this simulation. But this one had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ODEs running inside each cell. Those cells synchronized by contact and by chemical fields. When you load network models, you have a variety of scopes. We mentioned global models. There's a command to load into all cells, period. You could load by cell ID. You could load by cell type, all cells of a given type, and so on. This is just a summary slide in case you want to go back to things. Self.add antimony model to cell, model string equals, model name equals, cell equals, step size instead of cell equals, you could have ID equals, if you want to load by ID. If you want to load to all cells of a given type, it would be cell types and then a list of cell types, and so on. Model name is how CompuCell will refer to the model that you've loaded. Step size is that time unit conversion. You can also read Antimony or SBML or anything else from a file. In that case, instead of saying model underscore string equals model, you'd say model underscore file equals path. And so if you have an SBML model or an Antimony model or a CellML model that you've downloaded and included in your file path, you could do that. If you want to do stochastic solver, just add integrator equals quote Gillespie close quote inside the list of attributes. There are other attributes you can set, which I'm not going to go over today. You can look those up. You can also set initial conditions for the model. You could say initial conditions, variable S1 is something, parameter K1 is something. Again, this is in the form of a dictionary. We're used to that. Timestepping is just the simple call self.timestep SBML, open close parentheses. And all Antimony models are time-stepped together, but the time steps can be adjusted for each model separately. And if you want, you can look up the integrator settings under SBML global options. Again, to read and write, for cell and self.cell list, variable equals cell.sbml, whatever you called your model, quote, the name of the parameter variable, close quote. If the model is a free-floating model, instead of cell, you use self. If you want to assign, you just take cell.sbml.model name, quote, parameter name, and say it equals something else. You don't have to do gets and sets. It's possible to read all of the parameter and variables out. If you do result equals self or cell.sbml.modelname.values, that will return a dictionary with everything in it. So that's our quick review. Now we are going to build a delta notch model. Delta notch is one of the fundamental patterning mechanisms in biology. It's active very much during development. It's active during wound healing. It's active during homeostasis, and it's also active in cancer. Delta notch is a it's a paracrine mechanism. It's a contact mechanism, and it's a cross-inhibitory mechanism. So it tends to create checkerboard-like patterns. If a cell has high delta, it tries to make its neighbors have low delta and vice versa. Here we see human intestinal crypt cells. The red cells are expressing high notch. The dark cells are not. You see this alternating pattern. This is in zebrafish eye. You see alternating pattern that's going to determine which cells become photoreceptors. This is the same kind of pattern in Drosophila inner ear. And the same kind of patterning also affects vascular endothelial cells, blood vessel cells, and it's also important in cancer. The basic concept biologically is quite interesting. You have delta on one cell, it binds to notch on the neighboring cell. If notch is active, it inhibits cell specialization. Notch active in a cell inhibits delta in that cell. In general, you start out with some quasi-random pattern, and then one cell will have delta or notch win out and inhibit its neighbors. And so you get not a checkerboard where you have adjacency, but you actually get these gaps where you have a high delta cell surrounded by low delta cells. And so actually the geometry of the cell layout matters quite a bit in this case. The actual delta notch signaling mechanism is quite complex. We are going to use a very simplified model by Collier. which we can write down in about 2 minutes, we're going to assume that we only have within the cell delta active and notch. We're not going to model the difference between the delta and notch inside the cell and at the membrane, which are actually pretty important. And here's the diagram of what's happening. And here it is written as a form of ordinary differential equations. We haven't really talked about Hill functions and things yet, but here's this way this was read. The change in the delta inside my cell is a rate constant times 1 divided by 1 plus b times the notch level to the h. That is, if I have no notch, I produce delta at rate nu. As I have more notch, notch inhibits delta, so the production of delta goes to 0. If I had had more time, I would have talked about production models. You always have what's called first-order decay. That is, the degradation of any molecule has to happen. No molecule lives forever. That degradation is always proportional to the amount of the molecule you have. And so here we have degradation. If we start with D, it decays at a rate nu. Notice that production and decay are balanced, and so the equilibrium level, if we have no notch, is going to be 1 for delta. Our notch term is a more interesting one. Notch decays at a rate 1, but the production of notch is actually stimulated by delta, but not the delta in our cell. Delta with the D with a bar on top of it is the average level of delta from our neighbors. And so we have delta on my neighbors turning on notch in my cell. Notch in my cell turns off delta in my cell. Delta off in my cell inhibits notch production in my neighbor. Is that clear? Now the numerical values here that we're going to use, A of 0.01, B of 100, V of 1, K and H equals 2, those are things that you'll be able to play with later. Frankly, if I were going to write this model, I might have used a different scaling, but this is what Collier used in 1996, and so we'll stick with his choices. When we run this simulation, we get something that looks like this. Here's notch. We start out with a slightly random pattern, and we get high levels of notch in bands that surround low levels of notch where the delta is high. Someone asks, what do N, B, and A relate to? N is the level of notch inside my cell. A and B, A is a Hill coefficient. Delta turns off notch when its value is bigger than A. So if the amount of delta in my neighboring cells is bigger than 0.01, that delta will, delta turns on notch when delta is bigger than A. When the amount of delta in my neighboring cells is bigger than 0.01, then I turn on notch. K and H describe how steeply the switching behavior of turning delta and notch on and off is. The bigger K and H are, the steeper the turn on and off are, the more switch-like that behavior is. Value of 2 is actually pretty soft. It's almost linear. B is an equivalent scaling factor for notch within my cell. And I could have written this by dividing. I could have divided through by 100, and then I would have gotten something that was more parallel. If I divided by 100 over 100, then I'd get 1 over A plus N to the H, which would be parallel to this, and I'd have to rescale V. But because I set V equal to 1 to set the time scale, they did it that way. So this is the thing we're going to build together. Okay, so the steps in building models. when you're going to build models, especially a complex model, you want to think about the conceptual model and write it out, which we've done. And then you want to start building submodels one at a time. So for example, you might build the initial cell configuration and include basic cell behaviors like volume and contact energy and so on, and make sure that that works. It's not going to have any network models in it, but at least you know that that part of the simulation works. And then you're going to add one additional object class or mechanism or submodel at a time and make sure that it doesn't break things. Ideally, you'd like to make those submodels also executable independently so they can be tested. Sometimes that's easy to do. Sometimes it's harder to do. After each edition, you want to check your syntax and then run it, make sure your simulation does what you want. So you might start out by laying out your cells with no chemical fields, and then you might add a chemical field in diffusion, but not have it do anything with the cells. Make sure that that works. And then you add uptake of the chemical field by the cells and make sure that the concentration changes the way it should. That's what you did in the avascular tumor simulation yesterday. Then you might add cell growth with no cell division. Then you might add cell division. Then you might add an intracellular network, but not put it inside of the cells, just to make sure there are no syntax errors. And then you might load it into the cells, but not have it do anything, to make sure that that works. And then you might have it control the cell division process. If you build things in steps like that, when there's a problem, you know when the problem happened. And even though it seems slow to do things systematically, in general, it speeds up your development because you don't get stuck with errors you don't understand. Okay, so the steps in building a simple delta notch model are going to be create a two-dimensional array filled with cells. You'll use uniform initializer. You're going to type the model in Antimony. You're going to add the Antimony model to all cells. At each MCS, you're going to loop over each cell. You're going to loop over cell neighbors. You'll read the average value of D from the neighbors. You'll set the new value of D average, D bar, inside each cell based on the neighboring average, and you'll visualize the pattern of D and N. If you get stuck, you can load the completed model. It's exercise 5_2_2_delta_notch. So I would like you to do this. Please start out by creating a 42 by 42 by 1 simulation domain. Why 42 by 42? Well, because that gives me room for 5 cells. Impose volume, local flex, energy here. I said constraint. Use the uniform initializer to fill the whole simulation domain with cells of width 7. You know how to do that. You'll use Wizard to do this. In the steppable file, you're going to go through in the initializer and give every cell a volume of 50, target volume of 50, and lambda volume of 2. Use periodic boundary conditions on the cell lattice. That goes in the Wizard. Okay? That's your first step. I want to give people time to do that. Once you've done that, you're going to write the Antimony string corresponding to the ODEs. Then you're going to load the Antimony model into all cells. We'll randomize that initial configuration. We'll calculate the average, and then we'll create fields to display the values. Okay, so your first little exercise is just to create that initial configuration using Wizard. And you'll need to check the neighbor tracker box in that box of options, okay? There was a question in the chat about, is neighbor tracker called cell neighbors? It's called neighbor tracker. Here, line 32, plugin name equals neighbor tracker. Maybe it's worth my walking through this very quickly. Let's create a new CC3D project. Delta notch temp, because I've done this before. I said to make the lattice 42 by 42. I said to make it have periodic boundary conditions. Uniform initializer. I'm not going to play with the units here. We're going to create one cell type, which I can just call cell. I'm going to turn on contact, volume local flex. And yes, you're right. Here they've called it cell neighbors. I would also turn on the cell boundary pixel tracker. This 4.7 has changed the tick box name slightly. Let me see, do we need anything else? We need contact, we need volume energy, yes. That's all we need. Okay, next. Finish. So that's actually all we need to do. So if you want me, I can go back to the slide, but that's all you need to walk through. As I say, it's not too bad to did you see that, or did I not screen share that? Did you see Wizard run? So is it clear what you need to do here? There are quite a few steps, so I do want to move through it. I don't want to leave people behind, but I also want to make sure that we get through the whole exercise. In the Python steppable, you are going to have to set the target volume and lambda volume in the start function. So steppables are functions that are classes that are executed once per Monte Carlo step. There are both XML specified and Python specified steppable. But here, when I say steppable, I'm talking about the Python steppable. I should have said that more clearly. Okay, here we are inside of our new simulation, the one we just created here. I double click here on the name of the simulation. I find my Python steppables, which are here. I look inside of my Python steppables and I see on the start function, and the start function is empty. I am going to go in there and I'm going to go to CC3D Python, visit all cells. And that will give me 4cell and self.cell list. I now want to set the target volume and the target surface area. And I remember how to do that. But if I don't remember, I'm going to go to CC3D Python, cell attributes, and I'm going to pick lambda volume. And I'm going to pick target volume. In this case, I'm reading those out. I want to go the other direction. So I'm going to set lambda volume equals to, I think I said 2.0. And I said target volume, what did I say? 50, I think. 50. Now I'm going to hit save. Somebody says cells disappear. They shouldn't be disappearing. If you set the volumes correctly, you shouldn't be disappearing. Again, if you're stuck, you can download the code from here. So I forgot to do something when I did this. So a good point. Thank you. Which is, I actually didn't edit the XML properly. And so let me go back to the XML. When I have my uniform initializer, I'm drawing a box in the middle, and I want to fill all of my space with cells. So I'm going to set box min to 0. And I set my size of my lattice to 42. So I'm going to set that to 42. Try that. Does that help? Somebody run that and tell me whether it works. It's actually not wrong to have medium around the cells, but I wasn't intending that. So now we have our domain. And here, in fact, I have the indication of what we need to do. We need to add these 3 lines: for cell and self.cell list, target volume 50, lambda volume 2. And we needed to edit the box to 0 and 42, which I forgot to do. So if I'd read my own slide deck, I would have caught myself. All right, step 2 is we are going to write the antimony. And I'm going to give you a hint. J1 colon, nothing goes to X, semicolon rate law implements dx by dt equals rate law. J1 colon, nothing goes to D to the K implements d by dt equals d to the K. And so I need you to create at the beginning a little bit of code that implements this. So at the beginning, after you've loaded the basic things, but before the first class definition, you want to type something like model equals triple quotes, and then you'll be typing 1, 2 lines for definition of the simulate model, and then 3, 4, 5, 6, 7 lines to define the parameters. Okay, I'll give people a few minutes to try it out. Unfortunately, I don't have any code snippets that help you with antimony, but antimony syntax is pretty simple. Again, that's why I like it. It's also why I suggested people print out that one sheet, because the key thing is to remember that exponentiation here uses the caret rather than the double star. So no, this model will go at the very beginning of your steppable, after the first couple of lines where it loads various things. But before, you'll see a definition which will be called class. Put it above the class definition. This is in the region where you're defining parameters for the model. This is going to go here. This would be after line 3. After the from such and such import, after the import, you're going to put it here at line 3. It's actually not going to do any harm if you put it later, but it's most convenient to put it there. Let me see how I did it in my completed code. Actually, in my completed code, I put it in the start function. So you can put it in the start function too. So having said to put it at the top, maybe putting in the start function is a good idea after all. That's what I did there. If you put it at the very top, it's available to multiple classes, but in this case, we only have one class, so it doesn't. There's one little trick here, which is that D and D bar are different variables. So you're going to want to have a variable called D and another variable you could call D bar or D average, because these are separate things. So there actually are 3 variables here: D, N, and D bar. And if you want to make the H and the K parameters the same thing, that's fine. If you want to just set them equal to 2, that would be okay too. although it's sort of interesting to change the values and see what happens. The initial conditions we'll come back to in a minute. You could set them to 0 for the moment. I'll show that in the next slide. Actually, here I set the initial conditions to 1/2. We're going to overwrite those in the Python. So if you got it on your own, that's great. If not, you can copy it here. If you'd like, I can also paste this in the chat for people who are, so you don't have to take too much time on it. Again, I want people to learn, absolutely. On the other hand, I also want to make sure we get through the basic material. And so I don't want people to feel stuck. So there's a good question in the chat. Kaya asks, is it okay not to input initial conditions explicitly if we're going to override them in the start section? As a matter of practice with antimony, you're required to specify the initial conditions. And so I would always specify the initial conditions, even if you're going to override. This is based on the principle that this model should be able to run independently outside of the CompuCell simulation, so you can check whether it works. You must use here, this is a good point. Somebody listened to my lecture maybe too well this morning. Mark asks, should I use D average colon equals 0.4 or D average equals 0.4? Since we're going to change it at every Monte Carlo step. If this is a bit of a technical thing, which I didn't go into, I had several slides on it. If the only place D average shows up is inside a rate law, like line 11, then we must use the equal sign, not the colon equal sign. And I apologize for not going into that earlier. There's some subtlety to this question about when values are auto-updated and when not inside of antimony. And that was a really good, perceptive observation. If you use colon equals here, that will actually force the average to always be 0.5. And the result of that is when I overwrite it with Python, it will go back and set it to 0.5 inside of the antimony. Colon equals is right, is when a value depends on another dynamic parameter. That's right. Excellent question. And you just called for several slides that I didn't have time to show this morning. So now the next thing we have to do is add the antimony model to the cell types. And what you're going to do is in that initializer, we already have a loop that's setting cell dot target volume and cell dot lambda volume. After that, we're going to put our cursor there. We're going to go to SBML Solver, and we're going to go, actually, I'm wrong here because I'm doing it by cell types, not by cell. I said use SBML Solver, add antimony model to cell types. If I said add antimony model cell, then I would have said the right thing. That would go in the start function, but before you assign, not inside the loop. And we'll say self.add antimony model to cell types. And in this case, we're going to give it model string equals model string, whatever you called your string. You can give the model name something like delta notch. And then you'll say cell underscore types equals self, all capital letters, the name of your cell type. Alternatively, and I realize giving you alternatives may not be the most helpful thing at the moment, we could say add antimony model to cells and then do that inside of the loop. Let me do that here. You can then do it on your own. The way I suggested it in the slide was to do it for all cells of a given type. I didn't define my model here, so I better grab my model string, put it in. I had originally said to put the model string there. That would work. But people suggested putting it in the start function, so I'm going to do that. So that's there. Can people see the editor? Okay. Great. And now that I've defined that, I can either go here before my for loop, and I can go CC3D Python, SBML Solver, add antimony model to cell types. Lots of text here that I don't need. We're not reading from a file, so I have to get rid of that. We're reading from a model string. We just called it model string, so I don't have to change this. I have to give my model a name. I could call it delta notch. And my cell type, I have to go back and remember what I called my cell type. I think I just called it cell. I called it cell. So here I need to call it cell, all caps. Step size, I am going to set to be, I don't remember what I said in my slide. I'll make it 0.1. I'm not going to use initial conditions or integrator. So that's would work. Try running that and see if it works for you. The alternative would be to go here, CC3D Python, SBML Solver, add to individual cell. Again, I get a bunch of junk here, which I don't want. And now I'm going to say, the reason there's an if cell here is because if there were medium in my system, I don't want to add the antimony model to the medium. And so if I iterate over all cells, I often have to do if cell to make sure that I'm not looking at a medium cell. In this case, again, I don't use model file. Use model string. I'm going to give this model name equal to delta notch. I better call it delta notch 2 if I'm going to do this because I'm loading it twice into the same thing. And I would say cell equals cell here because my cell is named handle is cell. The step size, again, that I defined was 0.1. Then I have to change my view a little bit so that you can see this on the screen. I'm not going to define initial conditions or integrator. And here I had failed to comment out some of the other things that I had. Okay. So you have two options. I said it should be 0.2. Okay. Right. Did that work? When people ran it, did that run or crash? And which one did you decide to do? Did you do it this way or did you do it this way? Either one is fine. All right, so here's how to do it again. I walked you through this already. Add antimony model to cells. We had to edit this to get rid of the extra text. The next thing we have to do is initialize the values of delta and notch inside the cells. So we're going to reference this. In this case, I called the model dn, not delta notch, whatever I called the model. Cell.sbml name of model, quote d, if that's what you call the variable, equals, and then we've loaded numpy, I think. So you can get a random number, np.random.uniform, parenthesis, min max, make min 0.9 and max 1. Right? And then in the step function, add the command time step SBML models. That doesn't need any editing. And check that runs. Again, if you're having trouble keeping up, load exercises 5_2_2_ delta notch. So inside that start function loop, you're going to add these two lines, cell.sbml dot whatever you called your model, square bracket, whatever you called D, equals np.random.uniform parenthesis 0.91. Let me know when you've got that working. And the key thing is after each step, what you want to do is check. I understand now with this issue with player, you have to kill player and relaunch it. But each time when you've made these changes to your code, save it, run it, and make sure that you know that it works. It's not going to do anything very exciting, but at least you know you don't have a syntax error. And if you do have a syntax error, you know exactly where you introduced it. So let me try that myself. So I have NumPy loaded at the top here. NumPy is loaded as NP already, so I have it available. And so here, I'm going to use that first load antimony model, not this one. I'm going to go in here. If I don't remember how to reference my variables in antimony, I do get SBML model, get SBML value for SBML in a specific cell. There we go. All right. And in this case, I called my model delta notch. So this will be delta notch. I called my variable D and N. So I'm going to call the first one D. And I'm going to set this equal to, and this is one of these things where ChatGPT would help you out. It's NumPy random dot uniform parenthesis 0.9 comma 1.0. You probably did not put the name of the cell type inside of square brackets. Somebody says when you use the add by cell type, you have to remember the cell types list is a list. If you're getting a syntax error inside of the model string, that means typically you have a typo in the model string. Usually that means there's an unmatched parenthesis. Lorenzo actually does delta notch modeling for a living. He's a researcher who does delta notch research. So here, I want to do the same thing for N that I did for D. It's relatively easy to get a parenthesis error. Cell G object has no attribute SMBL because it's SBML. If you have medium in your system, you can have an issue where medium is not a cell type like everything else. And in that case, you can filter by doing if cell outside here like that. if you want to be able to build a system where you don't have only cells, but you also allow medium, it's better to do it this way. Okay. And then in the step function, we are going to go to CC3D Python, SBML, and we're going to go time step SBML model. We don't have to do anything to that. Yeah, I don't think you can do multiple assignments. In Python you can, but I don't think Antimony allows that. So here would be my suggested code for the start function. And then in the step function, try this. Oops, pasted it twice. Is that working for people? It's a bit of a long model, so. On the other hand, when you've done this, you've really done something. So, Rodrigo, you have to put the name of the cell type in square brackets. Mark says you have to give the name of the model the name that you gave it. But I'll let people discuss this with each other in the chat a bit. So the templated text that the Python, the code snippets paste in has placeholders for the model name. So you have to give the name. I can come back to that and then I'm going to move on. Actually, I'm going to show you the code for it in a second. Here's the code. Notice I have given the model name here. I called it DN. In my code I typed for you, I called it delta notch. Cell types equals self dot cell A and capitalized in square brackets. And then for cell and self dot cell list, I put it inside an if cell.sbml.dn. I have to use that name here, numpy random. So no, the model name has to be whatever you typed model name to be. In this case, I happen to use capitals. In the one that I did in the code that I coded for you, I called it delta notch with delta and D and delta and N in notch. Capitalized. Whatever you typed here and model name equals, you type here, exactly the same. The next step, again, all of this is available to you, is to loop over cells, create a placeholder for the average, iterate over neighbors, check if the neighbor is not medium, read the delta level, add the value of D for the neighbors, keep track of the number of neighbors, normalize by the number of neighbors, and update the value of D average. It's actually interesting to keep track of the contact area and weight the contribution by the contact area. But I think we're going to be close to running out of time. And so I think in this case, I'm going to go ahead and give you code to do this. I'll show you how to do it. So in the step function, for cell and self.cell list, again, we could have an if cell inside of here. Average contact is 0. Number of neighbors is 0. For neighbor common surface area in self.get neighbor cell list. If neighbor average contact plus equals common surface area, number of neighbors plus equals 1. If the number of neighbors is not 0, we have the average contact divided by NN. And so this is the code we need. If you want to do that yourself, how would I do that? I'm first going to iterate over cells, visit all cells. The next thing I'm going to do is check if my cell is actually a cell. I'm going to do an if cell. The next thing that I'm going to do is iterate over neighbors. Like that. And I'm not going to type all of it now. You've got the code in the chat. Here I've created a placeholder. I've created a placeholder for each cell, which is the number of neighbors. And I've called it D average. AVG here. 0.0. If neighbor, and n plus equals 1. And D average plus equals. I need the common surface area. It's right here, common surface area. I need to know what the value of D is of my neighbor. If I don't remember that, I go to SBML Solver, get SBML value. I need the name of my model, delta notch. And the value D. Now I'm outside of my loop. I have to say if and n, because if they're not, if I had 0, I can't do anything. I don't want to divide by 0. And I say D average equals D average divided by NN. I make that float. And then I want to set the value in my cell. And this should have been neighbor, not cell. I want to set the value in my cell of D. So here, I set the value cell, delta notch D equals D average. I'm sorry, there was a question. What is the cell ID? Cell ID is the number associated with each cell. Each cell has a unique number. So we're not using that here. So there's a cell number 1, a cell number 2, a cell number 22. Okay, does this work? If this works, it should, you have the full model. The next thing and the last thing we're going to do, and then we're going to have the model finished, is we have to create a tracking field to display delta and notch. Tracking fields are a little bit confusing because they go after the init and before the class definition. So we're going to create a tracking field using the extra fields automatic tracking track scalar attributes. And we just have to give the name N and D. And there's a little bit of an issue because the tracking fields read the cell dictionary, not the SBML dictionary. So we're going to have to copy from the SBML dictionary, the cell dictionary. So we're going to do that this way. We're going to add 2 lines. Cell.dict D equals cell.sbml name of the file dict D. Cell.dict N equals cell.sbmldnn. And we're going to add the 2 fields, delta and notch. I'll do that for you on the screen, and then I'll show you this display, and you can come do that yourself. And then we'll have the full null. So the first thing I'm going to do is after the init, here, line 9, I'm going to add the tracking field. CC3D Python, extra fields, automatic tracking, scalar attribute. I'm going to call the field name delta and the attribute name D. I'm going to copy this. I'm going to create a second one for notch. Notch. And the last thing I have to do, and this is the place where it may not be so obvious, is that I have to, in my step function, and actually here, this should have been indented by 1 level. Sorry, 2 levels. I have to copy this value into cell dictionary. So I now have to go and you need this number here. So what am I going to do? I'm going to say cell.dict square bracket D equals that. I need to do the same thing for the notch. What is this doing? I'm tracking cell.dict D, so I have to copy the value from the SBML solver into my cell dictionary. Okay. I'll give you the code in the chat. And if people can try running that, let me know if it works. Can somebody paste a picture from their simulation in the chat? Here's the code completed. Again, if you're stuck, you can download the completed code. If you're getting a single color and it's not changing at all, if you look in the bottom left-hand corner of these plots, where it'll say min and max value. If the min and max value are both 0, something is wrong. If the min and max value are different and you're seeing a constant color, that's because the scale for your field isn't set right. And then you have to go to settings and change the scale of the field. You have to display, for people who are not seeing it, remember you're going to have to select to display delta and notch. If you display the cell field, you're not going to see anything. Van asks what to expect. I think I showed at the very beginning this checkerboard pattern of delta and notch. So if you look at what people are getting in the chat, I think that looks really good. Rodrigo says attribute error, delta not steppable object has no attribute time step. That suggests to me a typo when you paste it in the time step. To avoid this kind of problem, I strongly recommend using the code snippets. That way you don't get so many syntax errors. Okay, let me run this for you. Okay, this is the initial configuration. This is a slightly later version of the simulation from the one I've got with you. I'm going to use tile to display things. Notice I have cell field and cell field. They don't show anything. I pull down here and select notch. I pull down here and select delta. Now I'm going to hit run. And I get the colors. Let me hit pause. If I look in the corner here, min value is 0.01, max is 0.96, so I know I actually have real values. If I was not getting something from delta and notch, I would go up here to configuration, field, notch field, and make sure that the min is fixed at 0 and the max is floating. Hit OK. Min and max values are quite high compared to the working ones. I'm not sure. Here I go from 0 to 1. Possible one of the numerical values you set was slightly different. When you typed your model definition, if you changed that value of V or nu in it, it will change the scale. Everything will still work, but the scale will be different. I'll let people work on this. I don't think we're going to have time, unfortunately, to do the other exercises, but I do want to show you a few things. So I appreciate your patience if I walk through these and leave them as homework assignments for you. You should be seeing something like this. Most people seem to be getting that. I'm not going to do this for you, but I will tell you that, Noshin, we always are available both before and after the sessions. So if you want to stay on after we're done today, we're happy to debug with you. CompuCell provides some tools for making movies. It's a little buggy. I couldn't get the actual movies to make. I can make the individual screenshots fine. I'm going to skip this slide, but just tell you, reference this slide for the instructions for how to actually save movies of your fields. The other thing that I'm not going to be able to talk about today that I really would have liked to be able to go over with you, and we can come back to, is we've talked about changing the values of parameters from that model editor, but only parameters that are set in the XML can be changed that way. If you want to change values in Python, you can use what are called steering panels. In this case, you have to decide what it is you want to change the value of. And Player will then pop up a window that allows you to change the values in the Python. However, doing that takes a little bit of work. You have to create the steering panel window, define the parameters, variables to be modified, define a function that watches for panel updates and reports them. This is called event-based programming. I don't know how many people have done that, or callbacks. And then you have to change the values of the updated parameters. And the simulation I've been showing here, 5.3.2 underscore delta notch steering, has this panel for changing the values of the coupling. And I'm just going to show this very quickly. And I'm going to, I'm going to not have you do these exercises. Between the init and the start function, the same places we added our tracking function, you're going to add a function called def add steering panel, and that's in the code snippets under steering panel, set up steering panel. And within that, for each parameter you want to change, you give the name of the parameter, the initial value, the minimum allowed value, the maximum allowed value, the decimal precision. Is it 0.1, 0.01? Is it an integer? And then whether it's going to be a slider or a pull-down menu. The next thing you do is you define a process steering panel, a function called process steering panel. This is called whenever the user touches that steering panel, and it reads the values that the user sets up in the steering panel. In this case, we're going to say A equals self.get steering parameter A, B equals self.get steering parameter B. And that is given in the twidit get updated value steering parameter. These are local to the function, and so if you want to use them outside of the function, you're going to have to save them in that shared steppable variables or global. In the step function, you can do things like while self.get steering parameter simulation type equals select simulation. This will pause the simulation until the user actually selects what simulation to run. You can also read values from the steering panel in the step function or at the beginning and adjust the values from that. In delta notch, what are the things we might want to change? A and B are the strength of inhibition and activation of delta and notch, respectively. So you might want to change those values. We can do that by adding a steering panel for A and for B. And we know that the allowed values are between 0 and here about 0.2, or between 0 and about 200. Then we have to have a function that processes that. We read the value of A and B from the user, and we reset the values in our cell of A and B. Now you can change the strength of activation and inhibition of the cells and see what kind of pattern you get. If I run this simulation, you'll see I have A and B here in my panel. If I click on those, it'll allow me to type in or slide new values, and the pattern will change. And I'm sorry that I don't have time to have everybody do that exercise on your own. It's an interesting, if you're running things in batch mode on a cluster, it's not something you're going to do. But if you're going to design tools that people are going to use to explore, instead of having to edit the parameter values, you can allow them to enter the parameter values through the screen. So that's something that I think you might want to look at. Another exercise that you might want to think about is that high levels of notch promote cell growth. Instead of filling my whole simulation with cells, I could start with 2 cells, have the cells grow at a constant rate and divide a constant double volume. And you'll actually see the pattern changes a lot when you do that. And then you can have the level of notch actually control. You can actually have the level of notch control the cell growth. And that's quite an interesting simulation to do here. And I think that that's worthwhile. If you want to try that out, there's completed code for that as well. Another thing to do is to try changing the spatial arrangement of the cells. That has quite a variety of effects. Linear chains have very different delta notch properties from compact clusters of the kind we're doing. In vascular growth, there's delta notch signaling between cells in a linear chain. That has a big effect. It's also quite interesting to make that delta average proportional to the contact area, not just to the number of contacts. And so those are a couple of things that you might want to try out. I also want to point out that there's a lecture I'm not going to get to give today. It's lecture 8.4 from 2023. It takes this delta notch model, which is rather abstract, and uses a model that was developed by a group at Notre Dame that has a very detailed model of calcium signaling between cells. And this is an oscillation of calcium signaling that happens in Drosophila early development. And you can generalize the delta notch model that we've done here to represent the calcium signaling in early embryonic development. That's what I had for today. You'll have the slides, you'll have the examples, and I hope maybe over the weekend people can work through this. And I'm happy to take the time after this lecture to sit down with anybody who wants to and help debug. And this year we decided we'd have 2 days off so that people had time to rewatch old material, catch up, maybe actually get some sleep. But this is quite a serious model. I mean, when this was done a few years ago, it was a research publishable model. And as I mentioned, Lorenzo Veschini, who's been helping us as a TA and will give a lecture next week, he's actually been doing research work when he was at King's College London. He was doing experimental work in vitro on delta notch signaling, where he had rather complex cell geometries that changed in time. And he saw oscillations in the delta notch signals. Now, he was using a much more detailed model of the delta notch signaling, not the simple Collier model. I mean, more sophisticated versions of this delta notch model are still current research topics.